So we'll now look at a remedial measure of autocorrelation, and to start things off with, we'll first write the regression model. So regression model is yt is equal to b1 plus b2 xt plus ut. Yeah, by the way, this the reference text for this remedial measure is Gujarati chapter 10, section 10.4 and 10.5. Okay, so this is the regression model, and we also assume that since we are dealing with autocorrelation problem, it must be a case that this ut term, the disturbance term, must be a function of its past error term. So we assume a AR1 scheme. We assume an AR1 scheme. AR1 scheme. So basically this becomes ut equal to rho times ut minus 1 plus vt, and rho takes a value between -1 and +1. Let's call this equation 1, and let us rewrite this AR scheme, this autoregressive 1 scheme, as Vt is equal to ut minus rho times u times t minus 1 as equation 2. Okay. Now let us rewrite this regression equation, the first equation, with the lag dependent variable. So let's say that in previous period, okay, in previous period, we can rewrite this equation 1 as yt minus 1 is equal to b1 plus b2 xt minus 1 plus mu t minus 1. Okay, multiply both sides, multiply both sides by rho. Okay, so when we do that, we'll get rho times t minus 1, rho times t yt minus 1, b1 rho plus rho times b2 xt minus 1 plus rho times ut minus 1. Okay, let's call this equation 3, and now we must subtract 3 from 1. So 1 minus 3. So let's rewrite this equation. So it becomes yt minus rho times yt minus 1 is equal to b1 times 1 minus rho, and here it becomes plus b2 times xt minus rho times xt minus 1 plus vt. Okay, now so there is one assumption in this AR1 scheme, which is that this vt, the error term here in the AR1 scheme, satisfies all usual OLS assumptions. Okay, satisfies all usual OLS assumptions. Okay, now you'll ask me why have I written here vt. Okay, so basically I've skipped a step, but let me just write one. Let me just also not skip the step here, so it becomes much clear to you why I've written vt. So if I just write if I just do this term minus this term, I'll get rho times ut minus 1 minus ut, and from this equation 2, okay, I can write this entire thing, rho times ut minus 1 minus ut, as vt. Okay, now all I can do is that I can just I can estimate this equation by OLS. Let me rewrite this expression yt minus rho times yt minus 1 as y star equal to b1 star plus B2 times x1 star, and this last error term is Vt as it is. And remember, this satisfies our OLS assumption, the usual OLS assumptions, and this term is no more autocorrelated with the past error terms. So in a way, uh, both these parameters, the estimates of both these parameters are OLS, are blue, and they can be estimated by OLS technique. Estimated by OLS technique. Okay, OLS technique. So the transformation equation y1 star is equal to beta 1 star plus beta 2 star x1 plus Vt uh, is also called, not R, is also called generalized difference equation, and the estimator of this equation are also called the GLS estimators. Now remember, even though we are estimating this equation by OLS technique, uh, well, we haven't really introduced formally what is GLS. So GLS is basically generalized least square technique, and it's not a part of your course. So for time being, we'll have to make peace with this term only. We won't be really explaining what do we mean by GLS. So basically, when you apply, just one moment. So when you apply OLS to this model, we basically get the estimators which will be very similar to the one we would get had we applied generalized least square technique to this initial model. Okay, and just one correction here, this should be 1 over here, y1, it should be y1 star. Okay, so okay, coming back to this slide. So note that earlier transformation can be applied to regression model of equations with can also be applied to regression model or equations with more than one explanatory variables and or higher order AR schemes. So basically, if you notice, we've taken only one explanatory variables x1, but we can include multiple x variables as well, and the results really won't change much. Okay, and we can also look at the higher order AR scheme. So for example, the scheme that we were looking at looks something like this: ut is equal to rho times ut minus 1 plus Vt. Okay, let's call this rho 1 instead. But we can also use different, you can say, so this was the AR1 scheme because we were looking at a lag of this one lag of this residual term or error term. We can also write this as rho times ut minus 1 plus rho 2 times ut minus 2 plus Vt. And remember, now we're looking at we're going for as far as the second lag of this residual term, and we have these two parameters to be estimated in this model. Okay, so we can proceed to higher order AR models as well. So we'll call this AR2. So nothing stops us from estimating a model wherein we have the higher order AR schemes or more than one explanatory variables. Okay. The only issue with this transformation is that we lose one observation, and that's pretty obvious because you're taking first difference. So when you look at the first difference, if I just quickly show it to you over here, let's call this yt and let's call this yt minus 1. Let me say this is 10, let me call this 9, 10 again, 11, and let's call this 5. So if I write here the yt minus 1, remember there is no term before 10. Okay, so this will be blank. Okay, this will become 10, and this 9 will come here, 10 will come here, and 11 will come here. So if I take a first difference, if I say let's create a new column over here, and I take, say, I'll write here yt minus rho times yt minus 1. Okay, so the first you can say block, or the first observation will be actually nothing. It won't be 0, it will be nothing, it will totally blank. Okay, so but for the remaining of them we can fill them. So in a way we are losing out on one observation. Now this can really matter if your sample size is really small, because if your sample size is really small, then you are losing out on one observation, and then your results might not be very you can say reliable. So what do we do in such a situation? In such a situation, we can use the Price-Winston transformation. So what do we do here? We basically express the y1 star as 1 minus rho square times y1 and x1 star as 1 minus rho square times x1. So we don't need to we don't need to do a, you can say, a first you can say a difference of yt and yt minus 1 that we have done in the previous slide. All you have to do is just plug this expression over here, and likewise for x1 star, plug this expression over here, retain this beta 1 star, um, and then you go on to estimate this model by OLS. In such a situation, you won't lose the observation that you would lose in this generalized difference equation transformation. Okay, but what is the challenge now? The challenge is how to estimate this rho. How to estimate this rho? Remember, rho is basically nothing but it's coming from your AR1 equation only. So basically, rho is something like this. It's coming from this AR1 equation, and in next lecture or recording, we'll discuss how to estimate this rho. Okay.